Alright, in this video we are going to answer this question about concavity. So we're looking at this function f at x equals x cubed minus 2x squared. We want to determine the intervals of concavity and the point or points of inflection. So it might only be 1 point. So in order to do this first part, determine the intervals of concavity, you have to first look at the second derivative. So determine the second derivative of x. So that would be step one. So in order to do that, you have to first find f prime. So f prime is 3x squared minus 4x. And then the second derivative is 6x minus 4. Okay, so the second part is to figure out the zeros of your second derivative. So let f double prime at x equal 0. So 6x minus 4 equals 0. So 6x equals 4. X is 4 over 6, or x equals 2/3. So that's the point where the second derivative is 0. Now you want to figure out where the second derivative is positive and negative. So in order to, there's a few different ways you can do that. One way, and the way that I usually suggest because it works, no matter what the example, is to just do an interval table. So the interval table is going to go from minus infinity to this point here, where the second derivative was 0, and then from there until infinity. And because we only have one point where the second derivative is 0, there's only sort of one dividing point, so there's only two intervals. And then you just look at the sign of the second derivative. Notice this is a lot like the first derivative test, where we were figuring out where the function's increasing or decreasing, but we're doing it on the second derivative. Sometimes we'll call this the test for concavity. So now you just want to figure out if the second derivative is positive or negative in these intervals. So you would take a number between minus infinity and 2/3. An easy number would be 0. So if you sub 0 into the second derivative function, so that's this one up here, if I subbed in 0, I would get a negative number. Right? 6 times 0 minus 4 is negative 4. It's a negative. Then in the next interval, if you subbed in a number bigger than 2/3, so like 1 is an easy example, subbed in 1 to this second derivative, you get a positive number. So from what we talked about before with concavity, if the second derivative is negative, that means you have a function, or the function is concave down. And if the second derivative is positive, then you are concave up. Okay, so therefore f at x is concave down, if x is in this interval here from minus infinity to 2/3 and concave up, if x is in the other interval. So that would be from 2/3 to infinity. Okay, so that's your intervals of concavity. Now we also want to figure out, part B was to look at, going back to the top here, part B was to figure out the points of inflection. Well, remember, the points of inflection occur when the function changes concavity. So we know that the function changes concavity at this point to x equals 2/3. So point of inflection if x equals 2/3, and the reason that happens is because it changes from concave down to concave up. So to get the point, we actually have to figure out the coordinates. So we need the y value. So the way you get the y value is you go back to the original function, x cubed minus 2x squared. So y will be equal to x cubed minus 2x squared. So f at 2/3, we'll just sub in 2/3 cubed minus 2 times 2/3 squared. So that'd be 8/27 minus 2 times 4/9. And now it's just getting common denominators. So 8/27 minus, that'd be 8/9. So we'll have to get a common denominator of 27. So multiply this by 3. So that'd be minus 16/27. So therefore the point of inflection is the x value is 2/3 and the y value is minus 16/27. So that's your point of inflection. Okay, so we have our intervals of concavity, where it's concave down and up, and our point of inflection. Okay, so that's the answer to the question. If we wanted to kind of see what this looked like, and this will be the next step, you could also go ahead and graph it. And I'm going to do a super rough sketch of what this looks like, just so you see the point of inflection and the concavity. Remember, the function was x cubed minus 2x squared. So if I want to graph, might help just to get the x-intercept. So that would be setting the function equal to 0. So x squared equals x minus 2. So I have an x-intercept of 0 and 2. So 1, 2. So I have an x-intercept there and there. My point of inflection was at 2/3 negative 16/27. So 2/3 is 2/3 of the way between 0 and 1, so about there. And negative 16/27, that's a little more than a half. So right around there, we've got our point of inflection. Okay, so then we know that the function was concave down to the left of 2/3. So it's going to be concave down over here and concave up over here. So what this function must look like, it's cubic. So it's going to be coming down like this. It's going to have a minimum point somewhere around here. We could actually figure that out. But then here, notice that's concave up. Now it's going to switch to concave down. Probably shouldn't look quite that messy. So it's coming down, hits its minimum, concave up, and now it switches to bending down. So it would look something like that. Okay, so notice concave up, concave down here, hits the point of inflection, and then changes to concave up. So that's how you graph or that's sort of what the graph would look like. The next thing we're going to do is kind of put this all together and actually use first derivatives to get the max and min to graph completely this function a little more accurately.